Here we're asked, does the following improper integral converge or diverge? And we have the integral from negative infinity to 0 of x e to the x dx. Now we're told explicitly that this is an improper integral, but even if we weren't, we would know this because we have this negative infinity as the lower bound of the integral. So to get a sense of what we're being asked here, let's just quickly look at the graph of this function. So here in blue, I have the graph of the function, x e to the x. And what we're interested in is we're interested in the definite integral from negative infinity to 0. So what this is asking us then is for the net area bounded by this curve between the x values of negative infinity and 0. So if I were to shade that area in, it'd look like this. Except it continues on to the left here forever. So this function, x e to the x, has this horizontal asymptote here at y equals 0. So as x goes to negative infinity, this function is going to get closer and closer to the x-axis. So what we're looking at is we're really looking at an infinitely long region. And when we ask ourselves if this integral converges or diverges, we're asking if this integral is going to give us a finite numeric value or if we're going to get an infinite area bounded by this curve here. So let's look at how we would actually figure this out. So the way we approach these improper integrals when we have an infinite, what we call an infinite interval, is we rewrite this as a limit. So I'm going to write this as the limit as I can pick any letter I want. I'll use the limit as a goes to negative infinity of the integral from a to 0 of x e to the x dx. And then my next step is going to be to actually solve this definite integral. And then once I get something in terms of a, I'll take this limit as a goes to negative infinity. So let's concentrate on how we would solve this kind of definite integral. Hopefully this looks a little bit familiar to you, this x e to the x dx. This is a perfect candidate for the integration technique of integration by parts that we studied recently. So remember, when we're using integration by parts, we want to choose u and dv. Now often we're going to choose u to be some polynomial expression, so x or some power of x or some x expression. So here I'm going to let u equal x, and I'm going to let dv equal e to the x dx. Once I've chosen that, then I need to compute du and v. Okay, so du is going to be the derivative of u, which in this case is going to give me dx. And then to get v, I'm going to actually take the antiderivative of e to the x dx, which in this case will just give me e to the x. And then integration by parts says that the integral of u dv equals uv minus the integral of v du. So then if we apply that here, I want to always make sure to carry my limit with me throughout. And then I'm going to put our integral work just in brackets for now. So then I'm going to rewrite this integral as uv, so that's going to be x e to the x, and ultimately we're going to evaluate that from a to 0, minus the integral from a to 0 of v du, which here is e to the x dx. Now this new integral, e to the x dx, is really easy to compute. So if we continue and actually do that, we end up with x e to the x minus, and then this second integral is just going to give us e to the x, and we're evaluating that all from a to 0. So now our next step is going to go ahead and plug in our bounds here. Once again, we're going to keep carrying this limit with us throughout the process. So if I plug in 0, I get 0 e to the 0 minus e to the 0 minus, and then I plug in a, I get a e to the a minus e to the a. Now we can simplify a little bit. 0 times e to the 0 is just 0, of course, and then I have minus e to the 0, which is 1. So I've got this negative 1 minus a e to the a, and then minus a negative, so plus e to the a. So now that I've got this all cleaned up and simplified, it's time to think about taking the limit of this expression as a goes to negative infinity. And that's actually not going to be trivial in this case. This expression is a little complex. So let's take advantage of the fact that we can split up limits and think about this term by term, since it is a little bit complicated. So I'm going to write this like this. And two of these limits are actually going to be pretty easy to think about. The first one is just the limit of a constant. So the limit as a goes to negative infinity of negative 1 is just negative 1, of course. And then this last one, the limit as a goes to negative infinity of e to the a, that's just going to be 0. Right, I can think about this power getting large in the negative direction. That's going to give me a really, really big denominator of a fraction. So that's going to approach 0, or you can think about what the graph of e to the a would look like and think about it that way. But anyway, this middle limit, this limit as a goes to negative infinity of a e to the a, is the one that's going to be a little challenging for us. So let's actually just look at that limit out to the side for a minute. So what's going on here? Well, as a goes to negative infinity, of course this a part is approaching negative infinity, but we just said that e to the a is approaching 0. So what we have here is actually an indeterminate form. Hopefully you remember this from when we studied this before. This is an indeterminate form, and a way we can evaluate this is by using something called L'Hopital's rule. But first, to use L'Hopital's rule, we need to rewrite this so that we get the form 0 over 0 or infinity over infinity. And there are a few different ways we could do that. One way is to write this as a limit as a goes to negative infinity of a over e to the negative a. Right, so I've just rewritten e to the a as an e to the negative a in the denominator. And if we look at the form of this limit, the top is going to be going to negative infinity. And in the bottom, what you can kind of think about here is getting an e to the negative infinity, which would be e to the infinity. So that's getting really big. So we've got this infinity over infinity form that we need to be able to use L'Hopital's rule. Now, what L'Hopital's rule says we can do is say this is equivalent to the limit as a goes to negative infinity. And then what I'm going to do is I'm going to take the derivative of the top and the bottom separately with respect to my variable a in this case. So if I take the derivative of the top, that's just going to give me 1. If I take the derivative of the bottom, that's going to give me negative e to the negative a. So then this becomes the limit as a goes to negative infinity of negative e to the a if I bring things back up to the numerator. Now remember, once again, we just said a second ago that the limit as a goes to negative infinity of e to the a is 0. So this, again, is just going to give us 0. So then what I end up with over here is negative 1 minus 0 plus 0, or just negative 1 in the end. So then in response to the original question, we can say that this improper integral converges. And that means that this area actually converges to a finite value, which in this case is negative 1. Here we're asked to evaluate the integral from pi over 3 to pi over 2 at tangent of x dx. So the first very important thing to realize here is that this is actually an improper integral. So how do we know that? Well, we can know that if we know about the tangent of x. You should know that the tangent of x has a lot of vertical asymptotes, and specifically it has a vertical asymptote at pi over 2. So since pi over 2 is within the bounds of our integration here, that tells us that we have an improper integral, and specifically an improper integral with what we call an unbounded integrand. We say it's unbounded because on this interval, we're going to have values approaching infinity or negative infinity. So let me show you a graph to show you in a little more detail what we mean here. So here I have graphed the tangent of x in blue, and remember that we're looking at the integral from pi over 3 to pi over 2 of tangent of x dx. So here's pi over 2, and I've sketched in my vertical asymptote here, and pi over 3 is somewhere in here. And so we're looking to find this area in here. Okay, so hopefully you can see why this is called unbounded, right? Because on this interval of integration here, my y values are not bounded, right? They're approaching positive infinity here. So I want to see if this area maybe equals a finite value, or maybe it diverges. So let's go back to the integral. So we're going to approach this in the same way we approach other improper integrals, and that's by rewriting this using a limit. So remember from the picture we just looked at that this vertical asymptote is on the right-hand boundary of my interval of integration here. So what I want to do is I want to take the limit as I approach that coming from the left. So then what I've done is I've replaced that pi over 2, that upper bound, with just some letter c, and then I'm going to take the limit as c goes to pi over 2 from the left. So then our next step is going to be to actually evaluate this definite integral. And I'm just going to keep this limit out front and carry it along with me. So the antiderivative of the tangent of x is actually the natural log of the absolute value of the secant of x. And we're going from pi over 3 to c. So if I plug in those limits of integration, I have in here the natural log of the absolute value of the secant of c minus the natural log of the absolute value of the secant of pi over 3. Now we can go ahead and evaluate the secant of pi over 3. So we know that the cosine of pi over 3 is 1/2. Okay, so that tells us then that the secant of pi over 3 equals 2. So now what remains for me to do is actually think about what this limit is going to give me. Now, it might be a little bit easier for us to think about things in terms of cosine, since we're a little bit more familiar with that. So I'm going to rewrite this a little bit. I've just rewritten the secant as 1 over the cosine of c. So here our c is approaching pi over 2 from the left-hand side. So we're approaching pi over 2, but from values that are slightly less than pi over 2. So we'll kind of think about this from the inside out. First, let's think about what's happening to cosine of c as c goes to pi over 2. Well, as c goes to pi over 2 from the left, cosine of c is just approaching 0. Right, cosine of x is just a continuous function, and if you know the values, you know that the cosine of pi over 2 is 0. So then this piece here, this denominator, is approaching 0. So what does that tell me then about the fraction as a whole, the fraction inside this natural log? Well, if the denominator of a fraction is approaching 0, then that fraction as a whole is going to approach infinity. So then what we know is we know that the argument of this natural log is getting larger and larger and larger without bound. So what does that tell us about this term as a whole? Well, if we know about the behavior or the graph of the natural log, we know that as the argument gets larger and larger and larger without bound, then the natural log itself is also going to get larger and larger. So this term then is approaching infinity. And infinity minus 2 is still infinitely large, so we find that the answer to this limit is infinity. Okay, and that's actually the answer to our original integral here. Or what we might say is that this integral diverges. So this area here that we shaded in green just continues to get larger and larger without bound. Here we're going to take a look at the integral from 0 to 1 of the natural log of x dx. The first important thing to realize here is that this is an improper integral. The reason we know that is because we know that the natural log of x has a vertical asymptote at x equals 0, and 0 is part of our bounds here. So what we have then is we have something that's called an unbounded integrand. And all that means is that our function, the natural log of x, approaches either positive infinity or negative infinity on this particular interval of integration. So let me show you a graph really quick to show you visually what's going on here. So here in blue is my function y equals natural log of x, and remember that I'm interested in the integral of that function from 0 to 1. So if I were to try to shade in the area represented by this definite integral, it would be this region in here. But what's happening is that as x goes to 0 from the right, so from this direction here, we know that the natural log of x goes to negative infinity. And we could see that on our graph here. If we zoomed out even more, this would just keep the y values here would just keep getting smaller and smaller as x got closer to 0 from the right. So anyway, this green region here, I can't really show it well on my picture here, but this continues right all the way down forever and ever. And what we'd like to determine is then if this integral, which represents this area, converges to a finite value or if it diverges. So let's go back to the board. So what we need to do here with this improper integral is actually set this up as a limit. So I'm going to write this as the limit as a goes to 0 from the right of the integral from a to 1 of the natural log of x dx. And then my next step is going to be to evaluate this definite integral, natural log of x from a to 1. Now we've actually seen the formula for this in the past. The antiderivative of the natural log of x is x ln x minus x, and notice here I've just carried this limit along. Now if you don't remember that formula, what that actually comes from is integration by parts. And I've reviewed the derivation of that down here in the corner if you'd like to pause the video and look at that. But anyway, going from this step, now that we have the antiderivative, we can go ahead and plug in our bounds, still of course remembering to carry that limit along with us. So if I plug in 1, I'm going to end up with the natural log of 1 minus 1. Subtract, and then I'm going to plug in a, so I get a natural log of a minus a. So simplifying this a little bit, I should know that the natural log of 1 is 0. So then inside my brackets here, I'm going to get negative 1 minus a natural log of a plus a. And now I'm ready to think about evaluating this limit. Okay, so we can think about this expression term by term if we want. Some terms are going to be easy and some terms are going to be more challenging. Now, of course, this negative 1 here, if I take the limit of a constant, it's just going to give me a constant, so that term's just approaching negative 1. And this a term here is also pretty simple to think about. The limit as a goes to 0 from the right of a is just 0. Okay, so then if I kind of rewrite the limit, taking those values into account, I can write this as negative 1 minus the limit as a goes to 0 from the right of a times the natural log of a. And that's the one term that we haven't figured out yet. And this term's a little bit more challenging. So let's think about what's happening to each piece here. Well, as a goes to 0 from the right, this a piece is, of course, just going to 0. But natural log of a, as a goes to 0 from the right, if you remember what the graph looked like, that piece is going to be approaching negative infinity. So what we've got here is an indeterminate form. And if you remember, often L'Hopital's rule is a useful thing, or useful technique you can use for evaluating indeterminate forms within limits. But to use L'Hopital's rule, your form has to be either 0 over 0 or infinity over infinity. So you're going to need to see if we can rewrite this. I'm going to do this work out to the side. So let's take a closer look at this limit. So I'm going to rewrite this in the following way. Instead of a natural log of a, I'm going to write ln a over 1 over a. And that's algebraically equivalent. And now, if I look at the form here, my natural log of a on top is approaching negative infinity. And on the bottom, I have this fraction where the denominator is going to 0, so then the fraction overall is going to infinity. So now I have my infinity over infinity form, and it's safe to use L'Hopital's rule. Now the way I use that rule is by actually taking the derivative of the top of my fraction and the bottom of my fraction separately. And then I can say those limits are equivalent. So if I take the derivative of the natural log of a with respect to a, I get 1 over a. If I take the derivative of 1 over a, I'm going to get negative 1 over a squared. Okay, I can simplify this a little bit by rewriting this as, instead of division of fractions, multiplication by the reciprocal. So it looks like this reduces to the limit as a goes to 0 from the right of negative a. Which then we can see that that limit is just going to give us 0. So then, bringing that back up here, I can write down my final answer. This limit is just equal to negative 1. And this is actually the value then of this original integral we were looking at. So we would say that this integral converges, and specifically it converges to a finite value of negative 1. In this example, we're going to look at the integral from 2 to 11 of 1 over the quantity x minus 3 to the 1/3 power dx. Now there's something really important to realize here, and that's that this is actually an improper integral. The way you can recognize that is by looking at this function here and noticing that it's going to have a vertical asymptote at x equals 3. I've got this vertical asymptote at x equals 3, and then I notice that my bounds actually include that x value, right? My bounds are going from 2 to 11 here. So then this is an improper integral because our integrand here is actually unbounded on this interval of integration. So let me show you a graph really quickly of this function. So we see again here this vertical asymptote at x equals 3. And the area that's represented by this integral, if I try to shade it in green, is going to look like this. And what we want to do is we want to find the value of this area if it's finite, or otherwise say that the integral diverges. So whenever we have a vertical asymptote at an interior point of our interval, we're going to have to actually split up the integral. And so specifically, I've split up that integral at the vertical asymptote x equals 3. And then I'm going to proceed, as I do in the cases of improper integrals in general, I'm going to rewrite each of these integrals using a limit. So writing in those limits, we'll have the following. And note that you can pick any letters here. I've chosen A and B for my limits. So now I have the limit as A goes to 3 from the left of the integral from 2 to a of our integrand, and then plus the limit as b goes to 3 from the right of the integral from b to 11 of our integrand. And then all I have to do is actually evaluate these definite integrals and then take the limits. Now I have the same integrand both places here, so let's just figure out what that is out to the side here. So if I just look at the indefinite integral, I have 1 over the quantity x minus 3 to the 1/3 power dx. We can just do a little quick u substitution here and let u equal x minus 3, and du then would be dx. So I would have then the integral of u to the negative 1/3 power du, which is going to give me u to the 2/3 over 2/3, or 3/2 u to the 2/3 power. So 3/2 x minus 3 to the 2/3 power. So I'm just going to use that result up here with these definite integrals. So then I'm going to have the limit as a goes to 3 from the left. I want to make sure to always carry those limits along with me, of 3/2 times x minus 3 to the 2/3 power from 2 to a, plus the limit as b goes to 3 from the right of 3/2 times x minus 3 to the 2/3 power, evaluated from b to 11. So now I'm ready to plug in some bounds within each of these limits. So I'll get the following. Now let's look at each of these limits for a second. Now in this first limit here, I have some expression involving a, and then I have just minus a constant term. Now if we look at that expression that involves a, and we're taking a limit here as a goes to 3 from the left. And what I have is 3/2 times a quantity a minus 3 to the 2/3 power. So as a goes to 3, either from the left or from the right, it doesn't really matter in this case, what's inside those parentheses is going to go to 0, which in turn is going to make this whole term go to 0. So then from this first limit, all I'm going to be left with is this constant term. And then we have a similar thing that happens in the second limit, where b is going to 3 from the right. I have this constant term, and then I have minus 3/2 times the quantity b minus 3 to the 2/3. So as b goes to 3 from the right, this b minus 3 term here is also going to be approaching 0. And then the limit of a constant term, of course, is just that constant. So then I'm just left with, in the end, these constant terms. Now we can simplify this a little bit, because negative 1 to the 2/3 power is just 1. We can think of that as negative 1 squared, right, which is 1, and then to the 1/3 power gives us 1 again. And then 8 to the 2/3 power is 4. So we end up with negative 3/2 plus 12/2, or 9/2 in the end. So this particular integral actually converges to this finite value of 9/2.